Hey everybody. So just a quick lesson on what's called standard half cells or reference standard half cell. If you take a look at your reduction half reaction table here, again, just to point out a couple things, these are reduction half reactions, these are reduction potentials. All these numbers mean over here, as we've talked about before, is the ability that these half reactions have to gain electrons. And if something's really good at gaining electrons, then it's going to be really bad at losing electrons. And if something is really bad at gaining electrons, then it's going to be really good at gaining electrons, or losing electrons, sorry. Then what does this zero mean right here? And kids get sometimes confused by this because they say, well, does this mean that this substance here doesn't have an ability to gain or lose electrons? And the answer is no, it does have an ability. But what this is just an arbitrary set point. Okay, so an example I go through in class to illustrate this is I line the kids up in the room and I say, okay, let's line up everybody from tallest to shortest. And so we do that and I say, okay, well, if I say that the tallest person in the room is height 0, I make up some new measuring system and I just say, okay, this person's height 0. What is everybody else's height going to be that's shorter than them in the room? And everybody says, obviously, well, their height's going to be negative. Right. And what if we made the shortest person in the room height 0? What would everybody else's height be? And they would say, okay, well, all of our heights would be positive. And so this little analogy helps to illustrate this table in that this table is set up the same way. All we've done is we've set the hydrogen half reaction as the standard reference half cell. What this means is that it's just set as the 0. And that this reaction of copper 2 positive, for example, is 0.34 volts better at gaining electrons than the hydrogen half reaction. And so what you'll see is you'll see two different types of questions on this concept. First, you'll see questions where they will simply ask you, hey, if we change the standard reference half cell to be not the hydrogen half reaction, but this silver half reaction, then what would be the new electrical potential for, let's say, this half reaction underneath? And you can see that the difference between these two numbers here is 0.03 volts. So if this is 0, then this one would be negative 0.03 volts. That would be its new number. And then you can see every other number on the table would also change accordingly, making sure that the difference between each reaction is always the same. So that's one type of question you can see. The second type of question that you'll see is they'll actually give you a full redox reaction and ask you to calculate the new net electrical potential based on a new standard reference half cell. And the thing that kids get confused on this one is that if I'm calculating a net electrical potential, whether this number is 0.8 and this number is 0, or whether this number is 0 and this number is negative 0.8 volts, the difference between these two half reactions is 0.80 volts. And so if those are the two half reactions I'm using, doesn't matter what their numbers are going to be. I know that the net electrical potential for each redox reaction is always going to be the same because these numbers are going to represent the difference or the different abilities that they have to gain or lose electrons. And so an example I'll give you for you to do on your paper just at home is you can do this one. If I had, for example, the reaction for rusting iron, so it's this half reaction right here, which is oxygen and water, gaining 4 electrons to make hydroxide ions. And it's got an electrical potential of 0.4. And here's the reducing agent of iron solid. If this was to lose electrons, so then this oxidation potential would be a positive 0.45 volts. Then the net electrical potential for that reaction would be just positive 0.4 plus a positive 0.45, which would be a positive 0.85 volts. But if I said that the silver half reaction is now the standard reference half cell, so this is the 0, then you could change these two half reactions to have their new numbers and be correlated to the fact that these numbers are 0.4 volts away from each other. So this would be a negative 0.4 volts, and this would be a negative 0.85 volts down here. Then you can see that, or sorry, this one would be even a little bit different. Anyways, you can take those two numbers and you can combine them, and you'll see that the answer that you would get, whether with the new numbers or the old numbers, the net electrical potential would be the same. It would be a positive 0.85 volts. And so you can do that at home. You can try that out and draw it up. Do it with the numbers listed in the book, and do it with the new numbers if the silver half reaction was the new reference half cell, and confirm that the numbers are the same. But those are the two types of questions that you could see. Either they just would simply ask you, how does this half reactions number change if this is now the reference half cell? Or they could ask you, what's the electrical potential for the net electrical potential for this redox reaction if the reference half cell were to change to this half reaction? And that one is just trying to get kids to show an understanding that, hey, the net electrical potential doesn't change because the difference between the two half reactions is going to be the same no matter what the number is, or no matter what the zero is set as. So hopefully that's helpful, guys. If you got any questions, you can let me know. See you guys in the next video.